All right, so here we are on the applications for the power rule. This is where it gets really good because we can skip all the slow, exhausting limit definition math, and we can quickly do the derivative and get to the application, the useful part of it. All right, so we got P.T. Barnum is shot out of a cannon 10 feet above the ground with a velocity of 40 feet per second. The equation for his height at any given time is this equation right here, which you could have made that equation. It's the negative 1/2 gt squared, plus initial velocity times time plus his initial height, but I just made it for you to speed it up. All right, and then it says find each of the following. First one says, when will he hit the ground? This one has no calculus whatsoever in it. You could have answered this in Algebra 2 easily. All right, so when will he hit the ground? Well, his height when he hits the ground is 0. So I'm going to put 0 in for h and solve for t. So part A is no calculus whatsoever. Don't let the fact that we're doing calculus make you forget that, there's other answers in math. So I'm just putting 0 equal to my original equation because my height is 0 when I hit the ground or when he hits the ground. And I'm solving that for t. So you could graph this on your calculator and find the 0. You could use the quadratic formula and do it that way. I don't care how you do it. I graphed it on my calculator and just found the 0. And when you do graph it on your calculator, the graph looks something like that right there. And finding this point right here ends up being t equals 2.729 seconds. Okay. 29. There we go. All right, so that's just Algebra 2 stuff there. All right, that's when he hits the ground. Part B says find an equation for his velocity, and I give you a nice hint here, his rate of change at any given time. Oh, rate of change, derivative. That's what it should just have popped up in your head. Okay, so since this is a distance or height equation, when we do its derivative, we find the rate of change of height or distance, rate of change of distance. That's velocity. So when we do the derivative of this equation, we're finding a velocity equation. So let's do its derivative, which 2 days ago would have sounded like a big headache to you. Now it's like, okay, this will take me 2 seconds. H prime of t equals, I'm just doing the power rule. I'm going to take my 2 times the negative 16, and I'm going to get negative 32, and I'm going to drop that 1 degree, so it'll be t to the first. And then I'm going to do the power rule to the plus 40t. I'm going to take 1 times 40, and I'm going to get plus 40. And then I'm going to drop the t down a degree. Well, t to the 0 power is 1, so the t goes away. And then the derivative of the 10 is just 0. I'm not going to bother writing plus 0. Boom, we're done. There's the derivative. So this equation right here will give me the velocity at any given time. So C is pretty easy to do. What is his velocity when he hits the ground? Well, to find out his velocity when he hits the ground, all I have to do is plug his time when he hits the ground, 2.729, into the derivative. So I'm just plugging that into here, and I'm going to get negative 32 times 2.729, and I'm going to add 40 to that. So plugging that in really quickly, you can erase me if you want. I'm going to go ahead and take negative 32 times that 2.729, and I'm going to add 40, and his velocity is negative 47.328, and this would be in feet per second. That's going to hurt. I hope Mr. Barnum has a net, because that's going to hurt just hitting the ground at 47 feet per second. And by the way, it should make sense to you that it's negative because he's going downward when he hits the ground. So it would be positive if he were on this part of the graph. But since he's on the downward part of the graph, it's negative. The velocity is negative. That makes sense to me. All right, let's go to part D. Part D says, what is his velocity at 0.5 seconds. Okay, so this won't take long. All I have to do is plug 0.5 into the derivative equation because I want his speed. So I'm just plugging 0.5 into here. I'm not even going to write it out. Negative 32 times 0.5, and I'm going to add 40 to that, and I get 24 feet per second. Now that one's positive because he's going up on 0.5. He's still going upward 0.5 seconds after he's shot. All right, and then the next one is very interesting. It says t equals 1.25. So I'm going to do h prime of 1.25. All right, I'm still trying to find his velocity. That's why I'm putting it into h prime. I'm not trying to find his height at 1.25. I'm finding his speed at 1.25, his rate of change. That's why we're doing it, putting it into the derivative. So I'm going to take negative 32 times 1.25, and I'm going to add 40 to that, and what in the world? I get 0. Well, this one should make sense to you if you look at the graph. If you look at the graph, right here is the 1.25, and that happens to be, oh my goodness, look at that, right at the top of this parabola. So we got our parabola going on here. Right at the top of this parabola is where you get a slope of 0 all year long. To find max and mins, you guys were totally reliant on your calculator. Now you can find max and mins using derivatives. Because at a maximum point, the derivative is going to be 0 every time. And that's what's going on here. You just found that 1.25 is when he's at the top. So if you wanted his maximum height, you could take 1.25, put it into the original equation, and that'll tell you what his height is at that point. You didn't have to use your calculator to find a maximum this time. And you can do that on any graph. I mean, if you had any polynomial you could think of, if you had something that ugly right there, you could find each of these max and mins by taking the derivative and setting it equal to 0, because all of those tangent lines have a slope of 0. That's how you find max and mins. We'll cover that a little more later, but I just wanted to introduce that to you now, because that's pretty dang important. All right, let's go ahead and do one more application. Oh, I'm sorry, I didn't mean to go there. One more application here. This one, actually, we're going to leave a little bit of calculus here and go back to kind of our old method, because the AP Calc loves to give you tables like this and see if you really understand what derivatives are. All right, so reading this, it says a mass is bouncing up and down on a spring, hanging from the ceiling, so it's sitting there going like this. Okay, its distance in feet from the ceiling is measured by a strobe photography. Wow, each 0.2 seconds, given in the table of values below, in which t is the time in seconds. All right, so this is our time in seconds. All right, and this was in feet. I just want to mark that to keep it straight in my head. All right, and then it says estimate how fast y is changing at t equals 0.3 and t equals 0.5. All right, just to be fast, I'm going to do one of these. I don't think you need it. They both are done the same way. So I'm just going to do 0.3. So if I want to estimate how fast y is changing at t equals 0.3, well, how fast it's changing, I'll do a derivative. The problem is I don't have an equation here to do a derivative of. I could load all these into my stats, do a regression equation, and eventually get there. But I can also estimate this just using the chart. Here's how I can estimate it using the chart. Well, t equals 0.3. Well, that's between 0.2 and 0.4. So I'm just going to use 0.2 and 0.4 to estimate what's going on at 0.3. Because those two surround the 0.3. So I'm just going to do the slope between these 2 points, and that gives me a good estimation of what's going on at t equals 0.3. So I'm just going to do that. So I'm just doing the slope between those two. So I'm taking the y2 of 5.84. I'm going to subtract my y1 of 3.99. And I'm going to divide all that by the x's subtracted, the 0.4 minus 0.2. And I will get a very good estimation for my slope. So putting this into my calculator right now. And you can see this is pretty dang easy as long as you understand what rate of change meant. This one isn't too bad at all. All right, that gave me 9.25. So that's a pretty good estimate for what's going on at my t equals 0.3. And I guess to label this, it was the y's on top, feet, and then seconds on the bottom. I probably should label it feet per second. There we go, shows more understanding there. All right, and let's go to B. B says at time t equals 0.3 seconds, is the mass going up and down justify your answer? Well, there's kind of two ways you can do this. One way is you can look at the chart and say, well, at 0.2, it's at 3.99, and at 0.4, it's at 5.84. So obviously it went from 3.99 to 5. Well, it's going up. That's one way to do it. That would work. Another way to do it would be look at your derivative, your rate of change right here. It's positive, so it's going up. That's even easier. So I'm just going to put that up. And my justification, because the slope is positive at t equals 0.3. That's about as simple as I can make that answer for you right there. Okay, so there's a few applications for you. And this stuff, man, this power rule stuff is great because it just speeds up the process for you. That's the beauty of it. And that's why you're going to learn the chain rule, the quotient rule, and all these other rules we're going to throw at you, because they'll speed up the process of you using that slow limit definition of derivatives. So, all right, well, good luck on the homework. You guys and dolls, take care. See ya.